Welcome to another video for Stat 420. In this video, we're going to talk about two-way ANOVA. So continuing on with ANOVA, but talking about what happens if we want to add a second factor variable into this model. So there's definitely some familiarity here. We've talked about kind of this model where we have mu plus alpha sub I plus an error term epsilon, but now we're going to add beta as well to represent a possible effect related to a second factor variable that has j different levels. Okay, so again, we have alpha representing this first factor variable where we have I different levels possible. So alpha sub 1 is the effect related to group 1, or I should say level 1 of factor 1. Alpha sub 2 would be the second level of factor 1, etc. And then beta j is now going to be the effects from factor variable 2. So beta 1, first level of factor 2, beta 2, second level of factor 2, etc. Now this alpha beta term in parentheses is going to represent something called an interaction, which we're going to talk about in just a second. But yeah, we have I levels for factor variable 1. We have j levels for factor variable 2, or b, I guess is what's listed here. And then k, by the way, is going to be how many replicates we happen to have per group. So, so if we have more than one observation in each of these different combinations, then k is going to help us identify which observation of that particular group we're talking about. So what is an interaction? I just mentioned it here that alpha beta represents what's called the interaction term. So an interaction is what happens when the factor levels are not additive with one another. So in other words, if I was just looking at, say, comparing this factor variable with two levels, and I notice that, oh, well, the response is higher for A than it is for B. So the kind of the factor level here is going to be alpha sub 1 is going to be slightly above 0, alpha sub 2 is going to be slightly below 0. However, if I'm layering that on to another factor variable, so in this case, this other factor variable takes 3 levels, and it's represented by these 3 different lines, you're going to notice that I don't have the same effect between A and B because it depends on which level of this other factor variable is being looked at. So for this level, it's going down from A to B. For this level, it's going up from A to B. So in other words, there's some kind of interaction going on such that the effect of this level for factor variable 1 is going to depend on which level of factor variable 2 is also involved here. So there's an interaction between these factor variables. So typically, we recognize an interaction when we see kind of these overlapping lines. So additive would mean that everything is kind of parallel, that I can kind of see the same effect, that it doesn't depend on what's going on with the other level. However, these are cases here where we see some change in direction. We see a little bit of kind of crisscross with the lines suggesting that there is some kind of interaction going on. And this, by the way, this plot over here is just the same information. It's just switching which factor variable we put on which axis, which can, maybe help us, again, kind of see. We really only need one, but it's helpful to kind of look at two sometimes. So if that is an example of two factor variables that interact, I thought we could also kind of draw what it would look like if there was a truly additive model, meaning that there is no interaction. In that case, we might see a situation like this where we have A, we have B, and we have maybe this kind of maybe a decreasing movement from A to B. But then for factor B level 2, then maybe it's actually up here. But again, if it's additive, then we should kind of see the same decreasing direction. And then for the third level, if there's a third level for this other factor, then maybe it starts up here. But then again, we should see roughly the same kind of effect. So then you can kind of see that, that if this is kind of our alpha term down here, so if this is alpha, and then maybe we have kind of A, if I'm correct with my colors here, we'll call it B, C, and this is my other factor variable. Maybe this is what I call beta. This is my beta term. Then the effect on the alpha levels, if this is like alpha 1, this is like alpha 2, then alpha 1's a little bit above 0, alpha 2's a little bit below 0, and I see that same kind of effect across all three levels of the beta term. And then for beta, I see that it's kind of C has the lowest effect. B is somewhere closer to 0, but maybe a little bit lower than 0, and then A certainly has a positive effect. So if I'm thinking about that model, you know, maybe, you know, if I think about kind of this y sub ijk equals mu plus alpha sub I plus beta j plus epsilon I jk, I don't really need this interaction term because I can just represent what's going on with y fairly well just using an additive model with alpha and beta. I don't have to worry about kind of this interaction. Well, it depends on which levels are coordinating with which, so I need some term to kind of represent what that correction or that change is going to be. All right. So if we're fitting a two-way ANOVA with an interaction term, then we're kind of finding like a mean specific to the set of levels that we're looking at. So let's take kind of the simplest case here. We have two factors that have two levels apiece. Then each of these terms represents kind of my best estimate for the response variable, given that we're at level 1 of factor A, level 1 of factor B. It's going to be represented by this equation. If we have an interaction term, then we add it in here as well. And we would do the same thing for each of the other combinations. Again, there's still an error term, right? So there's still random noise at each of these places. So this is just kind of a mean term. It's kind of our best estimate, but also with recognition that there's going to be variation still. I don't know what I just did. I just like hit that against my glasses there. There's still going to be variation still within each of these levels. We just recognize that we can make better predictions if we take into account which level is at play for the observation that we're looking at. Now compare that to just not using an interaction term. It's still kind of the same setup here where I have a different kind of estimated mean depending on the combination of factors, but since it's an additive model, I don't need to add an interaction term to try to account for how the levels interact with one another. Occasionally, we might start with a two-way ANOVA, check the model, and realize that maybe one of these predictors just isn't adding anything meaningful to our model. So we run the ANOVA, we look at the ANOVA table, we look at the f-test for each factor and realize, well, maybe this one is helping, but the other is really kind of redundant or unnecessary. So in which case, we might just go with a one-way ANOVA and just ignore the other factor as a predictor here. So for example, if I just leave out factor B and decide that this isn't adding anything meaningful to my model, then I'm just going to have mu plus alpha 1, mu plus alpha 2 in both places. And vice versa, again, if I go with B and leave out factor A, then I'm going to have the same kind of mean term in both of those cases. Now, when we think about the process of model fitting with ANOVA, where we have two factors at play, we probably want to start with a full model, including the interaction term, and then judge whether or not we need the interaction term. So we can kind of look at the f-test for the interaction, decide if it's significant, or at least if it's low enough that we want to keep it, low enough that we feel like we have enough evidence to keep it, and we can keep it, or we can drop it, and then just check with the additive model next and see if that seems appropriate. I'm going to move my face back over here as well. So then we can go to the additive model next and decide if that is working, if both of the factor variables seem to be have appropriately low p-values for their f-tests. And then if we need to, if that doesn't appear to be the case, then we could look at factor A or factor B individually. And then finally, if we absolutely just don't find anything, we might just accept the null model and say, we don't really, like neither of these factors seems to be adding anything meaningful to this model. They don't seem to have significant effects, significant prediction on the response. So yeah, this is just kind of an ordering of kind of fitting the models and making those decisions. So testing for an interaction, we're not really going to get into the math as much as we're just going to say that that's what's going on. It is an f-test. There is some calculation going on. There is some sum of squares decomposition going on over here that we're not going to break down. All we really care about is that when we add these kind of factors in, that we are trying to explain variation in the response variable. And depending on how much variation we explain, we're going to get an F ratio to determine if that amount of variation being explained is more than we would expect by random chance by just adding in a term like this. So if our F ratio gives us a p-value suggesting that this is beyond what we'd expect by random chance, then we can keep it. If it's not, then we consider dropping it. Now the null hypothesis is going to be very similar here. I need to move myself again. The null hypothesis is going to be, if we're doing it for the interaction term, our null hypothesis is that the additive model is kind of our baseline, and the alternative is that the interaction term should be added, and that this is giving us some kind of predictive power, that there is some kind of significant relationship when we add that term. And again, we're kind of doing it for all of the interactions, so either all the interactions are 0, or there is at least one interaction that should be non-zero and is adding something to our model. So let's kind of look at this in context. I'm going to use the context of the problem used in the book for part of this section. So let's say we're doing an experiment and we have 48 rats being randomly assigned to receive one of 3 poisons, and then again randomly assigned to receive one of 4 treatments. And we'd like to know which combination of treatments and poisons seems to result in the longest survival for these rats. So we're going to do what's called this is a 3x4 factorial design. So we have 3 levels for one factor, 4 levels for the other. And we also have 4 replicates here, meaning that since we have 48 rats, we're going to have 4 rats per combination, per per factor combination, if that makes sense, right? So if I have kind of a 4x3 setup, 1, 2, 3, 4, 1, 2, 3, that would be 12 different combinations. So 48 rats randomly assigned across 12 combinations. It's going to give us 4 per combination. So that's why we say that we have 4 replicates, because that will get us to 48. So does the poison consumed or the treatment used affect survival, and how might we model this relationship? So again, we're going to kind of use this hierarchy to think through this. We're going to start with the interaction term and decide if the interaction term seems appropriate to include with a full model. So let's start by looking at the interaction plots and seeing if there seems to be any interaction going on. And to be honest, there is a little bit, but not a lot going on here. If it was truly no interaction, then we should see parallel lines. However, we only have a sample, and so we're going to get a little random noise going on here. Even if it was truly additive, we shouldn't expect perfectly parallel lines with our not very large sample. So I don't think there's any surprise that we're going to have a little bit of bumpiness going on in some of these. Though I do have to say, these do seem to be moving pretty similarly regardless of which treatment I'm looking at. I see a very similar relationship across poison 1, 2, and 3, where like all of them seem to show poison 3 is producing the lowest survival times regardless of the treatment. Poison 1 seems to be pretty consistently okay, and then poison 2 is a little bit more mixed. So really, this one right here is kind of the odd one sticking out, the one that doesn't follow the trend. Everything else seems to be pretty parallel and going the same direction. So it looks, I'm going to say it's very close to additive. Oops, I missed a word there. Very close to additive. So when we run this f-test over here, I would expect the p-value is probably not going to be super low, especially since it's only 48. Now, if I saw this trend with a very large number, like the really large sample size, maybe that would mean something more. But with only 48, a little bit of bumpiness I think is expected here. So I don't think the F value is going to be super low. And it looks like it's about 11.2%, which is, you know, definitely on the lower side, but not so low that we'd probably reject the null hypothesis. Usually we want to see like 5%, or more ideally what we'd like to see more like 1 or 2% to say that we have, you know, some clear evidence here that this actually has some relationship and that this isn't just some random chance correlation that we're seeing here. So yeah, for this reason, probably not enough evidence for an interaction between, and when I say, again, interaction between the treatment factors, that we see that going on. Oh, something else I just want to mention here. So if you're running this in R, if you use the asterisk, then it's going to use both of these predictors and assume that you want an interaction term. So that's why I get poison, treatment, and an interaction here. Now compare that over here. Oops, not that one. Sorry, I was going to write it in. So if I did not want an interaction term, if I just wanted an additive model, then I would do AOV, and then in this case it's going to be time tilde poison plus treatment, just like you would with the linear model. So use a plus sign if you want to use both predictors but no interaction. Use a star asterisk if you want the interaction term to be included. Something else that I'll mention here is that the F test for each of the predictors separately does seem to be quite low. And if we were to run this model again without the interaction term, they would still remain very low, suggesting that both of these factor variables do seem to be adding predictive power in survival time, that the poison used and the treatment used seems to matter in survival time. Now, we can also run a kind of an ad hoc pairwise test as well, like a Tukey test. And here we have it on just the additive model. So again, I kind of skipped a step here, but we ran the additive model. Both the predictors look great, so we're going to keep them. So now we can do this post hoc test to see exactly where these differences seem to be occurring. So it's not necessarily between 1 and 2, but we definitely see it between 1 and 3 and 2 and 3. Definitely consistent with what we saw over here, right? So 1 and 2 seem to give some pretty similar results, maybe 2 a little bit lower than 1, but 3 definitely seems to greatly reduce survival time. And we definitely see that going on here with the Tukey results, that the 3 combinations are significantly different than 1 and 2. Now, if we're comparing the treatment options, it's a little bit harder to know what's going on here. B and A definitely are different. C and B definitely different, right? So I'm just going to kind of underline, or I guess I'll box them. And then D and A, I think we can kind of point to a difference here. So maybe not quite as low, but certainly like it's just below 1%. So that definitely gives some kind of a suggestion of a difference. And if we go back to our interaction plot, again, if we're kind of comparing these, B definitely seems to have the highest. D is relatively close to the highest. A is consistently the lowest. C is somewhere in the middle. So C is kind of ambiguous, but I would definitely say A is pretty starkly different than B, maybe a little bit different than D as well. And I think we see that here. So A is different than B. C is different than B as well. And then A and D shows a little bit of difference as well. So that gives us a little bit of insight of where these differences are kind of emerging, which exactly poison or treatment seems to be the most or the least effective. You can also kind of notice here the difference, right? So, which differences kind of stick out. So B has the much bigger survival time as compared to A because it has a positive value if we do B minus A. So yeah, this is just kind of drawing us some extra insight about where those pairwise comparisons show those differences.